Okay, so I'm still waiting for the record. Okay, for chapter 3.3, it is about variation of resistance with temperature. So if you guys still remember, if I go back to one of our slide about factors that affect the resistance, if you guys still remember, we talk about the dependence on resistance with the temperature. So this is one of the factors that affect the values of resistance, but most of the time we assume that the temperature is constant except in this subtopic. So for subtopic 3.3, you will learn that the resistance actually depends on the temperature. So you need to be able to explain the effect of temperature. So when it says you need to be explained, means that you need to understand why when temperature is increased, the resistance is increased. And you need to be able to use the formula. This is the increase resistance increase is actually because of this. When the temperature increases, the numbers of free electron per unit volume in matter remains unchanged. So you can assume inside here, let's say if I have specific amounts of electron inside specific volume, the amount will remains unchanged, dia tak berubah. But then when the temperature increase, so let's say if this one being heated up, so temperature increase, what will happen is that the electron will vibrate more. So normally you can directly relate temperature with kinetic energy. So the higher the temperature, the electron become more restless and it start to vibrate more. So when it start to vibrate more, to be exact, it's vibrating at greater amplitude. And because of that, there's higher tendency for collision. So collision increase, and that's why the electron slows down. The electron flows slows down. So if you guys still remember from microscopic model of current, let's say this one is positive, let's say I put negative here and positive this side. And if you guys still remember, the electron will try to flow from negative to positive. But the thing is when the temperature increase, let's say this one vibrates more, and at the same time they try to move in that direction. So the probabilities of collision increases, which then slows down the electron flow. So the resistance in the metal increases. So anything that slows down the flow of electron, that means the resistance increase. So previously for resistivity, you can assume that it is due to like uh, something that is on the road, like a pothole or something, that one will block or will reduce the current flow or traffic flow lah. But in this case, the amount of traffic is the same, but because it vibrates more, it slows down the flow of electron. Okay, ada soalan tak so far about the reason why the temperature increase, resistance increase?
Tak ada sih.
Tak ada. Okay, this is the basic concept of the effects of temperature. So in your learning outcome, you need to understand this one. Dia tak complicated pun, dia simple je. Just that ada few points yang penting lah yang kamu kena tahu. And if the question asks you to state those points, you should be able to state. Okay, so obviously once you understand the concept there, now you need to be able to use the formula. Yeah. Okay, anyway. So you have one general formula where R equals to R naught, 1 plus alpha delta T. If you notice, this one is very similar with the last semester punya equation, which is about a length, length extension due to temperature changes. So if you guys still remember, we have equation L equals to L naught 1 plus alpha delta T. Sama je, cuma dia L naught. The difference here is R, and then the key difference is actually the alpha. So kalau previously we have alpha, beta, and gamma, this one we only have alpha. So it is actually linearly dependent on the temperature changes. So R here is initial, R naught is initial resistance here, and R is final resistance. So macam biasalah, delta T is change in temperature. So I'm gonna write over here. Okay, since this one is change in temperature, you can use Kelvin, you can use Celsius, it doesn't matter, because if you change to Kelvin, then you minus back, and then you still get basically the same change in temperature. And if you notice, the alpha here, actually we use the unit per Celsius. So let's say in exam, they ask you to calculate alpha, use the unit per Celsius. Whatever the value you get, just write it per Celsius. And then this formula, actually I can rearrange. I can write this one. Okay, maybe I can write it over here. This one I can rearrange to becomes R equals to R naught plus R naught alpha delta T. So most of the time you might have to use this formula instead. Yeah? If the question, normally the question which asks you to find the change in resistance. So I can bring this one back to the left hand side. So it becomes R minus R naught, which means that one is delta R. Okay. So if the question asks you to find delta R, change in resistance, you can use this formula. And if the question asks you to find the final temperature, final resistance, you can use this formula. Okay, like I told you before, it is linearly dependent. So you will expect the graph of R against T to be linear like this. Okay. And the gradient actually is the coefficient of resistivity. So alpha is coefficient of resistivity. Graph tu dia jarang tanya lah. And biasanya dia akan kasih change in temperature and they ask you to find the new voltage ke, the new resistance. So they try to make things a little bit complicated by not directly asking you to find delta R. Instead, they ask you to find delta I or delta V. But that one you have to find delta R first. So the difference between this chapter, this subtopic and other subtopic is that the question will specifically state that they have a change in temperature. So memang dia akan cakap, okay, ada perubahan temperature. So kamu memang tahulah itu adalah subtopik ini. You need to use this formula. Ada satu formula je, so shouldn't be a problem. Cuma sometimes student maybe dia confused bila dalam soalan tu dia tak sure nak pakai V equals IR biasa ke nak pakai yang ni. Biasanya combination of both. You have to find R first and then you have to use Ohm's law, V equals to IR. Ohm's law tu valid untuk all the chapter. Mana-mana chapter pun dia valid lah. Okay, let's try to look at the example. We have example 3.3.1 here. Okay, a copper has a resistance of 25 milliohm at 20 degrees Celsius. When the wire is carrying a current, heat produced by the current causes the temperature of the wire to increase by 27 Celsius. Okay, so in theory, if you're doing for your circuit, in theory, if the circuit has lots of resistance and the current flows for a period of time, normally they will have power loss in the circuit. So the temperature will increase. So I think So across the terminal of a battery. EMF in electric source, potential difference between points. Apa ni? I don't know what's that. I'm not sure apa yang dia nak cakap. EMF. Okay, it's okay. So logically, kalau kamu nak fikirkan EMF dengan potential difference ni, EMF tu dia kata dalam spec dia, sepatutnya dia dapat 1.5. Tapi bila kamu try to measure, actually you get something less. The reason is because you have internal resistance in the battery. Okay, you can consider a circuit consisting of battery cell that is connected by a wire to external resistor as shown in the figure. So, figure yang kat belah kanan ni, I can redraw that one to something more common for you guys. Okay. So, normally in exam, they will give you a circuit that looks something like this. Sometimes dia kotakkan macam ni, sometimes dia biar je macam tu. So, if you have a resistor that sit right next to the power supply, that one normally the internal resistance. It is represented by a small letter R compared to the resistor of a circuit which is capital R, and then the power supply is actually EMF here over there. Okay, if you measure the voltage across the resistor, you will get a value of terminal voltage. So this one across the resistor is the same value that you will get over here. Okay, kalau syllabus sama dia pakai terminal voltage tu dia pakai simbol VT. Tapi yang ni kita dah tak pakai VT ya, kita just pakai V, and to differentiate terminal voltage dengan EMF, we just use epsilon dengan V je. Tu beza dia. Simbol Yang ni macam tak kena pakai tu je. In reality, when a battery is supplying the current, its terminal voltage is less than EMF. So dia mesti lagi less lah. This is due to energy dissipation in the battery. So before dia keluar lagi, dia dah ada internal resistance, dia dah ada energy dissipation, and that one is due to internal resistance. Sometimes dia punya chemical kat dalam battery tu itself, dia dah ada internal resistance. Okay, the formula that you need to use is actually this one. Epsilon equals to I R plus R. And epsilon equals to V plus I R. Okay, sebenarnya konsep dia datang daripada something like this. So you have EMF, okay, sebenarnya konsep dia datang daripada something like this. So you have EMF, the supposed value yang supplier cakap ada, and then minus the one that is lost inside the battery itself. So maybe I can write this one as V loss first. Benda ni kita tak pakai simbolnya, saya just tulis je sementara. And as a result, we get V terminal. The one that you measured across the battery lah, bila dia dah keluar. So everything here happen inside the battery itself. Okay, the battery. So the one that you measured, yang VT tu adalah V ni. Saya just label je dulu sebab saya nak bezakan nilai V tu. So VL tu is the loss of voltage. Ataupun proper term is voltage drop inside the battery itself. V equals to IR, so I can replace this one with I and R. The reason why I use small r is because we are talking about internal resistance. Okay, voltage terminal outside here is actually will be the same with the one across the resistor out here. So if that one is capital R, then I can write this one with epsilon minus IR equals to I capital R. So I can rearrange this one and it will look something like this. Epsilon equals to IR plus IR. If I factor the I, then I will get the exact formula of this one. You don't have to derive it every single time, tapi saya just point out so that you can understand the concept. And then sometimes certain book dia pakai this formula. So jangan terkejut lah. Kalau kamu baca buku teks ke apa, kamu jumpa that formula. The concept is like that. EMF, the supposed value of the voltage, and then the voltage drop due to internal resistance. The one that you measure outside is actually after the loss due to internal resistance. Okay, so what is actually internal resistance? It's a resistance due to chemical inside the battery. So even before they go out, dalam battery tu mesti ada internal resistance. Mesti ada. So it's constitute part of the total resistance in a circuit. The EMF of battery is constant, but the internal resistance of the battery increases with time as a result of chemical reaction. But that one, dalam syllabus kamu kita tak berkira macam tu lah. We don't consider R2 changes. We consider R2 as a constant value. And the internal resistance also depends on the type of chemical material in the battery. So different battery has a different internal resistance. But one battery, for tak pasal voltage terminal, EMF dengan internal resistance. 3 kuantiti ni ada tak soalannya, tak faham?
So sir, EMF tu basically battery punya potential difference without connecting to a circuit. And does it only apply to power source or?
Yes, it need to be applied to power supply. EMF tu by definition is actually electromotive. Ya, saya baca balik. EMF stand for electromotive force, the force that push the electron. And the only force that push the electron is actually from the power supply itself lah. And then lagi satu soalan kamu tadi apa yang mula tadi? Lupa lah.
Does it apply to any other power source, macam DC power supply ataupun ke dia just only for batteries?
Different power supply pun applied sama lah. Sama juga. Tapi when we are talking about internal resistance, normally kita cerita pasal batteries lah. Power supply yang ada chemical reaction tu. Bukan power supply yang pakai box, something like that. So kalau battery they consider as internal resistance macam tu, biasanya dalam syllabus kamu, when we are talking about this one, we are talking about batteries. Senang nak fikir lah, senang nak imagine. Okay, ada soalan lagi? Kita tengok ramai terkeluar termasuk. I think maybe line kamu this morning not that good pun. Mugat, okay, mugat. Mugat dah tidur
okay,
ni.
sir, tadi ada
lagi.
terkeluar sikit. Tak tidur, sir.
Amrudin ada? Tadi dia ada. Dia keluar balik Oh, dah ada balik. Amrudin, are you okay? Okay, dah terkeluar balik. Nanti internet not that good. Ya, saya tengok internet. Arif. Arif maybe tak lama lagi. Okay. It's okay, nanti saya ambil attendance. And then for those yang keep on masuk keluar tu, don't worry lah, saya upload video ni later. Okay, we discuss a little bit more. Ada lagi sikit. I want to discuss about the example. Okay, example 3.4.1. Semua punya content semua ni. understanding the concept is one thing, but the actual calculation is important as well. So kalau kamu faham, kamu tak boleh kira, then you lost, memang banyak markah kamu hilang lah. And then kalau kamu tahu kira, kamu tak faham pun akan hilang markah juga. So these two things is important. So I hope you understand the concept of internal resistance tu actually daripada mana datang internal resistance tu. And then saya betul-betul harap kamu boleh bezakan EMF dengan terminal voltage. Student biasa confused tu EMF dengan terminal voltage. Okay, a battery has an EMF of 12 volt and an internal resistance of 0.05 ohm. Its terminal are connected to a load resistance of 3 ohm. Find the current in the circuit and the terminal voltage of the battery. So they ask you to find V and R. Okay, I can try to redraw. I can try to draw the circuit so that maybe you can see it better. You have a battery that has EMF 12 volt, so label straight away with EMF, symbol epsilon, 12 volt. Internal resistance 0.05. Normally internal resistance, you do it right next to the power supply there. Okay, and you label it with small r. And then you can see that the values of R tu biasanya memang kecil juga. Normally less than 1 lah, normally. But it depends on the size of the battery. So this is the battery. Yang battery tu tak perlu lukis pun. Saya just lukis sebab nak tunjuk kamu. And then it's connected to a resistance of 3 ohm. Ayo. Okay, R is equals to 3 ohm. Okay, that one is capital R. Sehingga dalam exam, dia kasih all in terms of words. So you have to represent with a symbol lah. Okay, now, the one that you measured, terminal voltage is actually the voltage across the resistor here. So use the symbol V there, okay? I can use a formula R plus R, and I can find the I straight away. And because the question wanted to find the current, so I can use this formula to find the current. So EMF is given. You want to find current, so it will be 3 plus 0.05. And I think you should get 3.93 ampere. Okay, for the second part, they want you to find the terminal voltage. Okay, you know that the current that goes out here is 3.93. So the same amount of current will pass through the resistor. So if I want to find the voltage here, I can use V equals to IR straight away. Okay, but make sure you use R is capital R too. Kenapa saya consider capital R? Because basically you want to find V here lah. So the across this resistor, so like that. 3. Alternatively, you can use V equals to epsilon minus IR. Or you can use from this equation, okay, or you can use this equation. So you can find the V inside this equation over here. So it depends on the given information. If let's say the question want you to find, it depends on the given information lah. Kalau macam ni soalan dia memang kasih all the values, so you can choose lah. Either you want to use right hand side punya formula or left hand side. Dia tak kisah, dua-dua boleh. Cuba kita tengok example lain. A car battery has an EMF of 12 volt and internal resistance of 1 ohm. The external resistor of resistance 5 ohm is connected in series with the battery as shown. So the diagram is similar to the one that I draw just now. Okay, you will see that the internal resistance, small r, is actually equals to 1. So this one, I think, considered big as already because reach 1. But this one maybe because of car punya battery, so that one is a big battery, so you expect the internal resistance to be big as well. The 5 ohm is actually over here, connected in series with the battery should determine the reading of the ammeter and the voltmeter if both meters are ideal. So they want to find the reading here and here. So you can use the same method lah. Macam previously, you can find current first, or you can find EMF straight away, it doesn't matter. Okay, if I want to find current first, you can use the exact same formula. Epsilon is given. You get I equals to 3 ampere. So 12 divided by 4 should be 3. Saya salah tulis. Should be 5 and 1. 3 tu soalan sebelum ni. Okay, so 12 divided by 6 will be 2 ampere. So once you get this one, the voltage over here is actually the same one over here. Sama. V dengan V ni sama. Because kalau saya arrange R ni kan, kalau saya letak dia dekat sini, maybe kamu boleh nampak yang dia sebenarnya adalah sama lah. Kalau kamu ada resistor kat situ, bacaan voltmeter dia mesti sama juga. So I can use V equals IR straight away. Across the circuit punya resistor, so I have to use R2 equals to 5. Okay, so you will see that the terminal voltage or the voltage that you can measure is actually 10 volt compared to the EMF which is given by the manufacturer or supply power supply manufacturer, which is 12. So the terminal voltage is a little bit less compared to the actual value. Okay, I just want to introduce a little bit on resistance and in series and parallel. About internal resistance tadi semua kita yang previous subtopic ada soalan?
Tak ada je.
Okay, tak ada.
Okay je sir.
Alright. So the next subtopic, resistance in series and parallel, I would like to introduce first about this subtopic, especially part derivation tu, and then about the technique to solve. Maybe saya rasa saya akan buat video kot for that one, so that, and then I will combine with the next chapter, next subtopic, which is about Kirchhoff's law as well. Kirchhoff's law as well here. Mana dia? Yeah. So Kirchhoff rules dengan example for resistors in series and parallel, saya akan buat video for that one because saya nak kamu tengok banyak kali. But for the derivation part, I will do it today. Simple derivation. Okay, resistor in series. Consider 3 resistors are connected to series in battery, to the battery. So obviously kamu dah jumpa kot benda ni. Kapasiti itu pun kamu baru jumpa, and kat sekolah semua kamu dah selalu belajar resistor in series and parallel. Kalau series tu dia sebelah-sebelah, kalau parallel tu dia adalah junction in between them. Itu in terms of the drawing. Oops. Okay. If you have resistors in series, you basically only has one loop. Dia ada satu loop je, tak ada junction. So the properties of a current, selagi dia tak jumpa any junction, the value will remains the same. Kamu boleh bayangkan circuit ni macam jalan, and current tu macam kereta. Katakan saya ada 5 ampere, so maybe kamu boleh bayangkan ada 5 kereta. Katakan ada 5 kereta going out here, and the same 5 car will pass through the resistor, and the same amount will pass through the second resistor and the third resistor, because there's no other road pun, dia tak ada jalan lain. So the whole amount will pass through the same circuit. So I can write here I equals to I across the first resistor equals to I across the second resistor, and then equals to I across the third resistor. And then if you have potential in series, so if you guys still remember, kalau the whole part here is 10 volt, this one could be 5, 2, 3. Okay, so that means total up, you still get 10, but because this one is series, dia terbahagi kecil-kecil lah. Kalau dia parallel, dia sama je semua. So itu properties of V dengan I ni kamu kena faham. I tu paling senang nak ingat. So biasanya saya suggest student saya fahamkan yang I tu selagi dia tak jumpa any junction, value dia akan remains the same. And then V tu mesti opposite to the I. Kalau I sama, V dia mesti tambah. Kalau V tambah, I sama. Sorry, kalau V sama, I tambah. Dia dua tu dia terbalik. So V here is equals to V1 plus V2 plus V3. Okay, if I want to find the effective resistance, I have to do combination of this. So in your learning outcome, you need to be able to derive how to find R effective. Ataupun R effective lah. Sometimes dulu panggil R equivalent, but nowadays kita panggil R effective je. So you take the one with the plus sign. Antara dua ni kan, kamu ambil yang tambah tu, you start from there. So V equals to V tambah tu. And then you substitute V equals to IR. So kalau we are talking about the whole circuit, so that means IR equals to IR1 plus IR2 plus IR3. Okay, this one because V equals to IR effective. If you are talking about the whole circuit, if you are talking about across the first resistor, it will be IR1. Second resistor, IR2. Third resistor is IR3. So the setiap satu tu represent by each symbol lah. Kalau across R3, dia V3. So I substitute inside here, and because that I is equal, so I can finally write that R effective is equals to R1 plus R2 plus R3. And if you have more, then just a dot. Okay, that one is for resistors in series. Okay, untuk parallel pula. Okay, imagine that you have 5 cars just now, and then they meet up a junction over here. So kalau kereta jumpa junction, dia akan berpecah lah. So normally we try to go to the least resistant. Tapi takkan 5-5 semua masuk sini. Kalau 5-5 masuk sini dah jam pula kat situ. So dia akan pecah seimbang lah. Seimbang as if dependence on the resistor. So katakan sini 2, 1, 2 contohnya. And then it could be 3, 1, 1. And it depends on the value of the resistor. But the key thing here is that the current is no longer the same. So current would be I equals to I1 plus I2 plus I3. So setiap kali dia jumpa junction, current punya behavior dia akan berpecah. Berapa nilai pecahan dia tu depends on the resistance. So macam saya cakap lah, if current is a plus sign, so saya rasa macam terbalik. Okay, if current is a plus sign, that means the voltage mesti sama. Oops. So saya cakap tadi lah, dia antara dua ni dia terbalik. Satu tambah, satu equal. Kalau kamu nak hafal, paling senang sekali kamu faham yang I, and then the V tu the exact opposite to the yang lagi satu, yang I lah. Plus ini adalah parallel, you can see actually boleh nampak pun. Kalau yang ni across here is 10, so here is 10, then here is 10, semua pun 10. And then bila kamu nak derive, kalau soalan suruh derive, kamu ambil yang tambah ni and then you start from there. So here in this case, tambah tu adalah I. So I can write I equals to I1 plus I2 plus I3. Okay. And then you know that since V equals to IR, so I is equals to V over R. For I total will be V total over R effective. Okay. For I1, it will be V1 over R1. For I2, it will be V2 over R2. For I3, it will be V3 over R3. Jadi kalau kamu tengok balik dekat sini, okay, this one actually I dia pun I across 1, across 2, across 3. Tapi saya kat sini saya dah samakan siap-siap, so saya tak tulis tadi. Tapi sebenarnya dia tulis, bila dia substitute ni sebenarnya dia ada lagi, tapi lepas tu dia potong sebab dia sama. So if I substitute inside here, it will be V over R effective equals to V1 over R1 plus V2 over R2 plus V3 over R3. Okay, since the voltage is the same, I can cancel out the voltage. Okay, so you will get 1 over R effective is equals to 1 over R1 plus 1 over R2 plus 1 over R3. So daripada sinilah datang kalau di dalam series, satu terbakar kat sini, so the whole lampu tak menyala. Kalau kita pakai sistem dalam parallel tu, satu terbakar, current akan pergi kat tempat lagi satu lah. So it doesn't really matter pun, dia still menyala dekat lagi satu tu. So satu je yang terbakar, satu je yang tak menyala. So kalau kamu perasan dekat rumah kamu, kalau kamu ada satu switch yang ada connected to a multiple bulb, kalau satu tu terbakar, yang lain tu still hidup. Because it is actually connected to a parallel. So parallel ni tak adalah semestinya dia kena duduk dalam bertiga macam tu kan. Dia boleh, as long as it is parallel, then should be okay. Okay, any question on series and parallel punya R effective? Ada soalan tak?
So far so good, sir.
No,
so far,
sir.
so good, Okay, you can try to do few of the tutorials, dah banyak dah boleh buat. Okay, macam saya cakap lah, so for our next class, yang kelas yang satu yang lepas ni saya akan buat recording. So kamu tengok jadi puzzle So saya nak kamu tengok banyak kali sebenarnya, especially part Kirchhoff punya law tu. And then our next meeting would be next week. Kita jumpa balik next week dekat Gmeet. And during that time saya akan, kalau kamu ada soalan, kamu tanya saya masa tu, ataupun kamu PM saya before that. Okay, so I think we stop here now sebab masa pun dah habis. So thank you everyone.
Thank you, sir.
Okay,
Thank you, sir.
alright.
Thank you, sir.
Thank you, sir.
Okay.